Hi, my name is Scott and welcome. This presentation is on lipids. As you see in this picture, there's a salmon patty and asparagus. Each of these have oils in them, omega-3 and omega-6 fatty acids that for us are essential and healthy in our diet. Since lipids have a very diverse role in our body, I'm going to cover a wide array of topics, starting with the structure and function of lipids, fatty acids, essential fatty acids, triglycerides, phospholipids, and sterols. Then I'm going to cover the digestion, absorption, and transportation of these lipids. I'm going to cover some lipids in foods, recommendations for lipids, and cardiovascular disease and risk factors for that disease. So this is a flow chart, or an organizational chart, if you will, of lipids, which consists of fats and oils. In the food service industry, they describe fats as being solid and oils as liquids. So the lipids I'm going to cover, like I said, triglycerides, phospholipids, and sterols. And the triglycerides will break down into fatty acids and monoglycerides, diglycerides, or triglycerides. And the fatty acids will break down into either saturated or unsaturated fatty acids. In the sterols, we'll look at how sterol will form our cholesterols and will form structures such as vitamin D, steroid hormones, and bile salts. And the steroid hormones, which are estrogen and testosterone. And as far as phospholipids, we'll cover mainly lecithin and go into that. So let us begin. Lipids, they are commonly referred to as fats. They are composed of carbon, hydrogen, and fewer oxygens than carbohydrates. If you remember, hydrate is water, so you have a lot of oxygen in there, and carbohydrates are water soluble. Since lipids have fewer oxygens, they are not water soluble, and they are more compacted than carbohydrates. So they do not dissolve in water. They are solid at room temperature, and oils are liquid at room temperature. And here the energy yield in lipids are 9 kilocalories per gram. So when we store fats, little energy is required to convert fats to stored body fats. For example, it takes approximately 2.5 calories of energy to store 100 calories of fat. And if you remember, 9 kilocalories per gram into 100 calories is around 11 grams of fat. So it only costs us about 2.5 calories to take these fats in. And here's a little picture where we bring in triglycerides to fatty acids into the cell, and they are compacted to triglycerides. Whereas it will take approximately 23 calories of energy to convert 100 calories of glucose, which is about 25 grams, 4 kilocalories per gram into 100. It will cost us about 23 calories to convert the glucose into fat and then store that fat as fat. And here, the glucose, you see, it will come into the cell, and it has to be converted. It will go into an enzyme, glucose 6-phosphate, and then it will have to go through that conversion, which costs us a little more energy. So in storing fats, basically what I want you to learn here is that it takes little energy to store these fats. Now, using fats as energy, when the body needs energy, epinephrine and glucagon, and as we see here, a picture here, it has epinephrine and glucagon and a couple other hormones like thyroid hormone and growth hormone that will stimulate hormone-sensitive lipase to start breaking down triglycerides into free fatty acids and glycerol. So when we need these hormones, epinephrine and glucagon, it will trigger the hormone-sensitive lipase, which is an enzyme inside the adipose cells, to break down the triglycerides to fatty acids and glycerol. At rest, the body uses the energy needs of the body at rest is about 60% comes from fats. And during light to moderate intense exercise or extended periods of food deprivation, fat stores may make a slightly greater contribution to our energy needs. Excuse me. Fat provides very little glucose, since only the glycerol, the backbone, a triglyceride, and we'll see here in a couple slides coming up, contains of a glycerol backbone and 3 fatty acids which are connected to it. So the only way we get glucose from that is through the glycerol. And the Academy of Nutrition and Dietetics recommends a weight loss of no more than 1/2 to 1 pound per week. And that is 250 to 500 kilocalories reduction per day in our current nutrient intake. Anything greater will also constitute a loss of muscle, bone, and water. A person can rarely use more than 1/2 pound of fat a day. Now, saying this, there is very integrated mechanisms that our body uses to conserve proteins, use glucose primarily for the brain, red blood cells, and nerve cells, and the heart. So we conserve the glucose primarily for the brain, and then we use fats whenever we can to try to preserve the glucose. The next 2 slides I want to show you will take you into a little more depth than actually what this class is, but it will help you understand a little more about the metabolic processes and the integration of each of these nutrients, these energy-yielding nutrients that we use. So starting off here, starting off with insulin and glucose. You know, we use our blood glucose, and once the glucose in our blood starts to decline, the insulin that brings the glucose into the cells will also start to decline. So the blood glucose and the insulin, they have a linear relationship. As one declines, the other one starts to decline. And when the insulin declines, there's an inverse relationship from insulin and glucagon, where the glucagon will start to increase, and glucagon will start breaking down liver glycogen. Since there is a limited supply of liver glycogen, it is a straight drop down to a depletion. So this, it takes anywhere between 12 and 24 hours, dependent upon your activity level. So after we get close to depleting our glycogen stores, then we start using plasma fatty acids, the fatty acids in our blood, and we start using those as energy. In extended long periods of time, the fatty acids will start to plateau. And then after a period of time, we'll start using ketone bodies. And ketone bodies are acetoacetate and beta hydroxybutyrate. These bodies come from an incomplete breakdown of fatty acids. And since fatty acids can't cross the blood-brain barrier, these ketone bodies can. Beta hydroxybutyrate is a ketone body. It's not a true ketone, but it's converted back to acetoacetate, which is a true ketone. And then the brain will take each of these in, it'll cross the blood-brain barrier, and it will break those down to acetyl-CoA. And acetyl-CoAs are what is cleaved off fatty acids, 2 carbons at a time, which will provide us with energy. And you know, it gets a little more complicated than this, and I don't want to go into much into this, but I did want you to see the relationship between insulin, glucagon, the plasma fatty acids, and then the long-term result of ketone bodies. So here, the first priority is to provide sufficient glucose to the brain and other tissues that are dependent upon it. Second priority is to preserve proteins and shift from utilization of glucose to utilization of fatty acids and the ketone bodies. The mobilization of the triglycerides in adipose tissues and gluconeogenesis by the liver, muscles shift from glucose to fatty acids as fuel. So then after 3 days of starvation, as you see here, the glucose starts to decline in our body. And for a complete oxidation of these fatty acids, we will always need some glucose. So we need to conserve glucose. But there comes a period of time when we will run out of our glucose, and then we'll start, you know, the fatty acids will start running out there, and then we'll be breaking down into ketone bodies, mainly for fuel, in long term. So after 3 days of starvation, the liver starts to form large amounts of ketone bodies. That's because an intermediate in the TCA cycle is depleted, so it starts building up these acetyl-CoAs. And they're released into the blood, brain, and heart to start to use ketone bodies as fuel. So after several weeks of starvation, these ketone bodies become the major fuel of the brain. And after depletion of these triglyceride stores, the protein degradation accelerates. You start using more protein, and these are very important for our tissues and organs. Death is due to the loss of heart, liver, and kidney function. So these 2 slides, I basically wanted to take you into a little more understanding of how we use different fuels at different times. Okay, for lipids. Lipids, again, they are triglycerides, phospholipids, and sterols. Triglycerides, again, it is a glycerol molecule with 3 fatty acids attached to it, and we will cover that. So I'm going to cover the triglycerides, phospholipids, and sterols. And fatty acids, first, the functions of fatty acids, they provide energy. As you just heard, fatty acids are built, they are synthesized at 2 carbons at a time. And, you know, it takes, if you're looking at a 16 carbon chain fatty acid, palmitic acid, for example, at 16 carbons. If you want to know how many ATPs it takes to build a fatty acid, it's not many at all. Like, it doesn't take much energy to store fat. It doesn't take much energy to build a fatty acid. So if it's 16 carbons long, you simply split that in half, which is 8, and you always start with 1 acetyl-CoA, so you can subtract 1. So it takes 7 ATPs to build a fatty acid. Now, when we have a complete oxidation of these fatty acids, specifically palmitic acid, it will yield approximately 106 to 108 ATPs. So there is a good energy release with a complete oxidation. So going further, it provides us with energy. It is an efficient storage form of energy in the form of triglycerides. So it has 3 fatty acids compact onto a glycerol. It provides insulation. Fat is a poor conductor of heat, so it insulates our body. It provides protection. It surrounds organs, and it provides protection in our joints. It is the transportation of fat-soluble vitamins. It provides some satiety. Satiety meaning it gives you a feeling of fullness. Since it has 9 kilocalories per gram, and it takes a little longer to digest fats than it would simple sugars, it makes us feel fuller longer. It gives food flavor and texture. Okay, fatty acids. They are mostly even-numbered carbon chains from 2 to 24 carbons in length with a methyl end and a carboxylic acid end, an acid end. And we will cover that. Long-chain fatty acids, they are fatty acids that are anywhere from 12 to 24 carbons in length, and examples of these are meats, fish, and vegetable oils. Medium-chain fatty acids are anywhere between 6 and 10 carbons in length, and they are mostly animal fats, coconut oil, palm oil, peanut oil, and some seeds. Short-chain fatty acids are very short. They are between 2 and 4 carbons in length. An example of these are primarily dairy products. Now, the shorter the carbon chain, the softer the fat becomes at room temperature. There is also a degree of unsaturation. That means the number of bonds, double bonds that it has. So the increasing degree of unsaturation also affects a fatty acid's firmness. Saturated fatty acids are carbon chains that are saturated with hydrogen. So we're going to go over this. They are solid fats. An example is animal fats. Monounsaturated fatty acids have 1 double bond, and they are liquid fats. And when you start to refrigerate them, they might start to gel and become a little semi-solid. And polyunsaturated fatty acids, they have more than 1 double bond, and they are liquid fats. An example here is corn, soybean, sunflower, and safflower oils. Okay, let's build a saturated fatty acid. First, we start with a carbon which has 3 hydrogens surrounding it. In the beginning, I let you know about methane. It was a carbon with 4 hydrogens around it. Well, this is a methyl. A methyl meaning it has the 3 hydrogens and 1 free electron ready to pair up to something else, kind of like the caboose on a train, if you will. Let's add some carbons to this. Here are 2 carbons. Now, normally, like I said, that fatty acids are built at 2 at a time. So let's do that here. Here are 2, 4, 6, 8, 10, 12, 14, 16, and the last 2, 18. Now, this last group here is an acid group. That's a carboxylic acid, and this is the methyl end. It is also called the omega end. So the omega end is with the methyl, and the alpha end is with the carboxylic acid. It is the acid end. Now, you can also see these long chains of carbon that drawn in a different way. They can look like this. This also has a carbon on each end, and at each angle it has a carbon. So this is also a 18 carbon chain, and we simply attach the methyl end here and the carboxylic acid there, and this is the same structure. It's just drawn a little differently. You don't have to draw all these carbons and hydrogens. And to even simplify this a little more, well, first, this is 18 carbons, and this is stearic acid. And to simplify it a little more, this is how it will look. I believe this is the most simplest form you can see. And the carboxylic acid is simply condensed to carbon, 2 oxygens, and the hydrogen. So I will show you more of these coming up. So this is the saturated fatty acid. This fatty acid, each one of these carbons are saturated with a hydrogen. Carbon, again, has 4 bonds, and around this carbon it has 1 bond to the carbon, another bond to the carbon, a bond to the hydrogen, a bond to this hydrogen. So this carbon is saturated with hydrogens. It can't take any more. Now this is a list of the saturated fatty acids, starting with butyric, caproic, caprylic, capric, lauric, myristic, palmitic, stearic, arachidic, behenic, and lignoceric, which is 24 carbons in length. So again, they are predominantly even numbered: 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and the longest one is 24 carbons in length. Excuse me. Now let's build a monounsaturated fatty acid. Mono means 1, and we're going to unsaturate it. We're going to take 2 of these hydrogens out. This is an 18 carbon chain, and what we're going to do is we're going to add 1 double bond. This is shorthand notation that chemists use to signify what we're looking at. 18 carbons, a colon, and number 1 for 1 double bond, then a semicolon, and where that double bond starts. So if we look at this, it has, at the 9th carbon, you will see a desaturation. You will take 2 of these hydrogens out, and we'll add a double bond at the 9th carbon. So here we have a monounsaturated fatty acids. It's 18 carbons in length, and this is, since it starts the double bond at the 9th carbon, it is an omega-9 fatty acid, and this symbol is omega. So this is omega-9 fatty acid, and it is oleic acid. This, again, is another form of it, is line form with the double bond on the 9th carbon, and you take out the hydrogen from each one of the carbons, and it will form the oleic acid. So this is a polyunsaturated fatty acid. That means more than 1 double bonds in this. We're going to start with 18 carbons again, and this is linoleic. It is an omega-6 fatty acid. So what we're going to do is we're going to put in a double bond starting on the 6th carbon. 1, 2, 3, 4, 5, 6. We'll take out, and we're going to put in 2 double bonds, since linoleic has 2 double bonds. 2 double bonds starting at the 6th carbon. So we'll take out those 2 hydrogens, and then we'll convert to a double bond. It is now a monounsaturated, but linoleic has 2 double bonds. So then we'll take out 2 more hydrogens and add a double bond there. Now this is linoleic. It is an omega-6 fatty acid, and we'll cover that more in depth coming up. And this is a more simplified structure. Okay, cis and trans fatty acids. You always hear, trans fats, but you don't very rarely hear about cis fats. What that is simply is whenever you build these carbon chains, on the double bond, you will see that you have a bond going to another carbon on the same side of the double bond. These are carbons on the same side, and the hydrogen will come off on the opposite side. So cis means same. It means the carbons are on the same side, and the hydrogens are also on the same side with each other. Now trans fats means that the double bond, the carbons are on opposite sides of the double bond, and the hydrogens are also on opposite sides of the double bond. Now trans fatty acids don't really occur naturally in foods. They are predominantly hydrogenated. Their hydrogen is infused into these oils, and they will start to form these trans fatty acids. But we'll cover that a little more coming up. So essential and non-essential fatty acids. Non-essential means the body can make double bonds only after the 9th carbon from the omega end. So starting from the omega end, 9 carbons over, you can make double bonds there, and that is non-essential. If the body if the carbons are past, if the double bonds are past, past the ninth carbon, the double bonds are past the ninth carbon, and those are in there, those are non-essential. But the body cannot make double bonds before the ninth carbon. So starting from the methyl end, like double bonds at the third carbon and the sixth carbon, which are omega-3 and omega-6s, we cannot make those double bonds. We don't have the enzymes in our body to synthesize those fats with the double bonds at anything prior to the ninth carbon. So those are considered essential. An example of those, again, are the omega-3 fatty acids, alpha-linolenic acid, and omega-6 fatty acid, which is linoleic acid. And the functions of essential fatty acids is they function in our immune system, vision, cellular membranes, and their production of hormone-like compounds. So let's start off with essential fatty acids. Okay, essential fatty acids, again, they are omega-3 fatty acids and omega-6 fatty acids. The omega-3 fatty acids are alpha-linolenic. That means they start with 18 carbons and they have 3 double bonds. And this alpha-linolenic, through a process of dehydrogenation, taking out hydrogens and elongating this 18 carbons to greater carbons here to 20, you desaturate and elongate this fatty acid and you end up with icosapentaenoic acid. And then you'll do the same, dehydrogenate, desaturate some of the hydrogens off this carbon chain and then elongate it again, and you'll come up with docosahexaenoic acid. So icosapentaenoic, penta meaning 5, it has 5 double bonds, and decosahexa, hexa meaning 6, it will have 6 double bonds. We'll cover these in more depth here in a minute. Omega-6 fatty acids, we're looking at linoleic fatty acids. Again, this is 18 carbons long, but it has 2 double bonds. And this is the precursor of arachidonic acid. Again, you will dehydrogenate, you will desaturate, and then elongate the 18 carbon chain and make the carbon chain longer and taking out hydrogen. So you will make that into a 20 carbon chain and 4 double bonds. So omega-3 fatty acids, again, this is alpha-linolenic acid. Now, there's a couple ways to look at this. First, when we say omega-3 fatty acids, we're counting from the omega end. 1 carbon, 2 carbon, 3 carbon. So this is an omega-3 fatty acid. Again, linolenic, it is 18 carbons long, and it has 3 double bonds. So it has a double bond at 3, 6, and 9, counting from the omega end. But scientists, they use systematic naming, from naming meaning nomenclature, how they name chemical compounds. And they do that through a systemic process through the IUPAC, International Union of Pure and Applied Chemists. They start naming these chains a little differently. They do it by prioritizing the properties of the chain. So this carbon, you would say this is attached to oxygen, whereas this carbon here is attached to 1 carbon and hydrogen. I'm sorry, it would be here. So that carbon would be attached to 3 hydrogens. So this has more priority. So in the systemic nomenclature, the way to name these, they will start on this end. So this will be 1, 2, 3, up to 9, 10, 11, 12, and they'll name it that way. But looking at this, there are 2 ways, again, to look at it. This is the omega shorthand notation, but scientists will also use this as 18 carbons long. It has 3 double bonds, and then it's at the delta end. This is the alpha. It has the omega and the alpha and the omega end. But when you're writing this, it is delta 9, 12, 15. So you have a double bond at 9, 12, and 15. So you'll see this in a couple more fatty acids that I have here. Basically what I'm pointing out here, this is an omega-3 fatty acid. It has 18 carbons in length. It has 3 double bonds. And there are two different ways to number it. One is from the omega end, and that's how we consider calling these omega-3 or omega-6 fatty acids, because that's where the first double bond is, starting from the omega end. Now, when you get scientifically, and we're not going to do that at this point, but I just wanted to point this out, that there are rules and processes that you go by in naming chemical compounds, and they will start from the acidic end and the alpha end, where the acid, the carboxylic acid, and that will be 18 carbons, 3 double bonds at the delta 9, 12, and 15. Now, normally you don't see these fatty acids in a linear structure. You will look at them more in a configuration like this, because in nature, the double bonds are in the cis configuration. So here we satisfy that, because this double bond, the bonds going to this next carbon and this next carbon are on the same side, and then what you don't see is the two hydrogens coming off there. So this double bond is cis, this is cis, and that is cis. So in nature, double bonds are mostly in the cis configuration in fatty acids. So another omega-3 fatty acids, as I was saying, the alpha-linolenic will build into an icosapentaenoic acid. And this is 20 carbons. It has 5 double bonds. And if we're looking from the omega end, 20 carbons, 5 double bonds, starting at, again, the omega-3 fatty acids. Now, if you're looking at it the scientific point of view and you want to do this systemic nomenclature, then you'll say it has 20 carbons, it has 5 double bonds, and starting from the alpha end, it will be delta 5, 8, 11, 14, 17. And again, here we have more of a natural conformation than this linear structure to point these out to you, is that this double bond is in cis, and each one of these double bonds are in cis. We can actually turn this into one big circle as long as it conforms to a cis configuration. Okay, another omega-3 fatty acid, this is the longest, this is docosahexaenoic acid. And it has 22 carbons in length, it has 6 double bonds, and it is an omega-3 fatty acid because from the delta end, 1, 2, 3, starts the first double bond. This here, it only has the names from the delta end. So let's go ahead and do that just real quickly. It has 22 carbons, 6 double bonds, and it's at delta from the acid end, the carboxylic acid, or the alpha end. It has a double bond at 4, 7, 10, 13, 16, and 19. And here you'll see that it has a more natural configuration. Each one of these double bonds, again, are in the cis configuration. Okay, sources of omega-3 fatty acids. They're primarily found in fish oils. Salmon, tuna, sardines, mackerel, they are all good sources of omega-3 fatty acids. The recommended intake for fish is 2 servings of fish per week, and a serving is 3 ounces. They're also found in canola oil, walnuts, flaxseed, mussels, crab, shrimp, and soybean oil. The health-related effects of these omega-3 fatty acids, the icosapentaenoic and the docosahexaenoic acids, they decrease blood clotting, they reduce heart attack, they decrease inflammation, and an excess of these fatty acids that thin the blood, they will cause hemorrhage stroke. In the brain, you have the vessels there, and the capillary walls may become so thin that you will start losing blood in an isolated part of the brain, and that could cause hemorrhage stroke. The blood is hemorrhaging from the vessels. Other possible uses, they lower triglycerides, they decrease rheumatoid arthritis, and they have a decrease in some behavioral disorders. So omega-6 fatty acids. Omega-6 fatty acids, again, they are called omega-6 because counting from the omega end, the double bond is at the 6th carbon. Now, this is linoleic, and it is an omega-6 fatty acid. It has 18 carbons in length with 2 double bonds starting at the 6th carbon. And if you want to look at the nomenclature, the scientific nomenclature, it has 18 carbons, 2 double bonds starting at the delta 9 and then 12. And this is a more of a natural configuration of the linoleic acid. It has each of the double bonds in a cis configuration. Again, you can see these probably in any different ways. It could be circled into a circle as long as these double bonds are in the cis configuration. This is an omega-6 fatty acid also. Like I was saying, linoleic will also be converted. It will be elongated. It will add carbons to this, and it will turn into a 20-carbon chain in length. It will have 4 double bonds, starting at, again, omega-6 fatty acids, starting from the omega end, 1, 2, 3, 4, 5, 6. The sixth carbon will start the double bond, and it has 4 double bonds. Now, if we look at the systematic nomenclature, it will be 20 carbons in length, 4 double bonds, and starting from the delta end, it will be 5, 8, 11, and 14. So this, again, is a more natural configuration in each of these double bonds in a cis configuration. Sources of omega-6 fatty acids are found in vegetable oils. We only need approximately 2 to 4 tablespoons a day, and you can also find these in beef, poultry, safflower, and sunflower oil and corn oils. Okay, health-related effects of omega-6 fatty acids. Arachidonic acid, it increases blood clotting, and it will increase the inflammatory response. So we may need this inflammatory response, and we need a certain level of our blood to clot. And I have recommendations at the end for these ratios, omega-6 and omega-3 fatty acids coming up. So essential fatty acid deficiencies, they will cause the flaky and itchy skin, diarrhea, infections, and retarded growth and wound healing. Now, this is a list of polyunsaturated fatty acids, starting with 16 carbons in length. When you had fatty acid synthesis and they're building these fatty acids 2 carbons at a time, this is what you'll get predominantly is the 16 carbon palmitoleic acid, oleic acid, linoleic, arachidonic, icosapentaenoic, and docosahexaenoic, which is 22, and the 24 carbons in length was on the saturated fatty acids. So they're from 2 to 24 carbons in length, and you will find the omega-3 linolenic in soybean, and also the omega-3Rs in seafoods. This is the casa and the docosahexaenoic and pentanoic fatty acids. Here is a comparison of the saturated fat to polyunsaturated and monounsaturated fatty acids. And if you here look briefly, you can see that safflower has the least amount of saturated fatty acids, and it has a good proportion of polyunsaturated fatty acids. So this is a very good oil. Canola oil, it has low amount of saturated fatty acids. Sunflower, corn oil, peanut oil, olive oil, all these, except it has a limited amount of poly, but it has a good percentage of monounsaturated fatty acids, so those are good as well. Now, if we look down on the other end of the spectrum here, we have coconut oil, which is very high in saturated fatty acids, and almost relatively no polyunsaturated fatty acids. Again, butter, palm oil, beef fat, and lard each have a large amount of saturated fatty acids. Okay, oxidation and rancidity. Excuse me. Rancidity is when the double bonds of unsaturated fatty acids are oxidized. So you'll have free radicals or something like that, or basically they can be broken down by UV light or oxygen. It causes an unpleasant odor and flavor to food. So what happens is these double bonds get broken down, and it causes this rancidity, which is an unpleasant odor and taste in foods. Polyunsaturated fatty acids, they are the most susceptible due to the increased number of double bonds. So there is a greater probability that these polyunsaturated fatty acids will become rancid. And this causes problems for food industry by decreasing the shelf life. Now, there are ways to help prevention of this rancidity, and one is hydrogenation. And this is what the food industry does. They infuse hydrogen into these oils, and it becomes hydrogenated fatty acids. So they add 2 hydrogens to a double bond, 1 hydrogen to each carbon, and you lose that double bond, and then it becomes a saturated fatty acid. And most likely it will become a trans fatty acid. And this double bond, it's used to solidify an oil. it increases the shelf life of foods and gives better qualities in food production. It leads to the formation of trans fatty acids, like I said, and trans fatty acids is a byproduct of hydrogenation of vegetable oils. And another way you can prevent this rancidity is by using antioxidants. Vitamin E and vitamin C each are natural antioxidants, and they will help protect these double bonds. So again, you'll have these free radicals that has an electron that is ready to hook up with something, and it wants to come in and take some of the electrons from the double bond and break that double bond. That's a free radical. It's looking for something to destroy or take. So vitamin E and vitamin C act as these antioxidants, and it pairs up with these radicals and eliminates the ability for these to break down that double bond. Also, there are synthetic antioxidants. There is butylated hydroxyanisole, a BHA, and there's butylated hydroxytoluene, and this is BHT. Each of these you can add these to foods and as an antioxidant to prevent the breaking down of the double bond for oxidizing the double bond, leading to rancidity. And also you can use airtight packages to prevent the oxidation. So triglycerides. They provide energy for body movements and in times of fasting. They are stored in muscles. Many cells in the body have triglycerides, especially the liver and the muscle cells. They act as protection. The fat pads serve as natural shock absorbers, providing cushions for bones and vital organs. That is deep inside the body. They surround the kidneys and the other organs. There's a large amount of fat surrounding these, protecting them from shock. And the fat that's deep inside the body is called visceral fat. It also acts as an insulator. Fat is a poor conductor of heat, like I said earlier, so the layer of fat beneath the skin, the subcutaneous fat right below the layer of skin, helps keep the body warm. And it helps use carbohydrates and proteins efficiency, kind of like what I went over earlier about the different rates at which we use the energy-yielding nutrients. And in the beginning, I basically told you that carbohydrates were our fuel source and fats were stored fuel, and we want to conserve the proteins. And then during the carbohydrate lecture, I let you know that carbohydrates help preserve proteins and fatty acid oxidation. So the triglycerides, they are the predominant form of fat in foods and the body. They are in plant and animal sources, and they are stored in adipose tissue. A triglyceride includes a glycerol. This is a glycerol molecule. It's 3 carbons, and it has hydrogens around it, and it has a hydroxyl on each one of the carbons. A hydroxyl meaning an oxygen and a hydrogen paired together. And then what we do is we hook up these fatty acids. The body will hook up these long-chain fatty acids, and they will hook up right here. The hydroxyls will pair up, just like we did in carbohydrates with the glycosidic bond. This bond here will join. Let me show you how it does that. The hydroxyl will come off the glycerol, and a hydrogen will come off the fatty acid, and there it will be condensed or dehydration. We'll lose a water here, an oxygen, and 2 hydrogens on each one of these fatty acids to the glycerol molecule. And then you will have the oxygen bonding each the glycerol and the fatty acids. So this is a triglyceride. It has 3 fatty acids bonded to a glycerol backbone. Now, a diglyceride is only 2 fatty acids bonded to the glycerol, and a monoglyceride is 1 fatty acid bonded to this glycerol backbone. Phospholipids. Phospholipids, most of them are built on a glycerol backbone that contain a phosphate. It contains a phosphate group. It contains fatty acids and additional compounds such as choline in the case of lecithin. So here we go. We have the glycerol backbone, and we have 2 fatty acids. In the case of lecithin, lecithin is the most well-known fatty acid. Phospholipid, excuse me. So it has 2 fatty acids bonded to this glycerol backbone, and it has a phosphate. This phosphate makes it hydrophilic. It loves the water. And the fatty acids are hydrophobic, and they don't like the water. And here on lecithin, it has a choline group, which together with this phosphate and the choline, this is the polar head. Here is a picture of a fatty acid, lecithin, which has the polar head and the nonpolar tails, nonpolar meaning hydrophobic, and the polar head is hydrophilic. So it will function in cell membranes, and it is used also as an emulsifier, and we'll come up on that in a minute. So here again, you have the two fatty acid tails, and on the opposing end, you have the phosphate with the choline group. And that will form the cell membranes and emulsifiers. So phospholipids, they are non-essential as they are synthesized by the body as needed. Supplementation is not necessary, and components of the body, such as parts of the brain and cell membranes, need phospholipids. It helps with the digestion, absorption, and transportation of fats, and they are contained in foods such as eggs, liver, soybeans, peanuts, wheat germ, especially the yolks and the eggs, and organ meats. The food industry adds phospholipids to foods to act as emulsifiers. So let me go over what an emulsifier is. Excuse me. Emulsifiers are compounds that allow fats to be suspended or mixed with water. Examples are bile acids and lecithins. I just showed you the picture of lecithin. This acts as an emulsifier. It helps us mix fats with water. The fats will be attracted into this micelle. It's a micelle. So fatty acids are soluble in fat, and the phosphate is soluble in water, thus allowing the suspension in the form of micelles. So water and oil do not mix. We all know that. And in a way to get it to mix, we use lecithin, which is a phospholipid. And these micelles, the lecithin will surround this fat globule, and in the water, the oil will be attracted to the center. It will be attracted to the fatty acid tails. And the water, it will help suspend it by this hydrophilic, water-loving head of the phosphate and the choline. So that will form a micelle, a circular structure that will have the fat in the middle and be surrounded by water. So you will have a bunch of these micelles, very small in the water, so it gives the appearance, and it actually is mixing in with the water. So that's what emulsifier does. Micelles are monoglycerides and fatty acids that merge together, forming a sphere of fat, which is emulsified, surrounded by bile salts. Sterols. Sterols are compounds that contain multiple carbon rings. Unlike fatty acids, they do not have a glycerol backbone. They don't readily dissolve in water, and they're a waxy substance. They're found in plant and animal foods, such as meat, fish, poultry, and eggs, and cholesterol is the most common sterol. Cholesterol is a component of cell membranes. As we learned, it is integrated into the phospholipid bilayers of cellular membranes. It is a precursor of bile acids, and it is a precursor of hormones, such as the female hormones estrogen, progesterone, testosterone, vitamin D, and corticosteroids. So this is a compound of cholesterol. It has 4 carbon rings, and it has a carbon chain on it. Now, cholesterol is a precursor of bile acids, like I just said, and basically you have a carboxylic acid put onto this carbon chain, and that becomes a bile acid. To turn it into a bile salt, you simply add a cation, such as sodium, to that acid, and it will become a bile salt. Cholesterol is a precursor of, again, female hormones, such as estrogen, progesterone, and testosterone for males, and vitamin D, and again corticosteroids, that they are involved in the stress response and the inflammatory response. Cholesterol, according to the American Heart Association, the liver and other cells in your body, they make about 75% of the blood cholesterol, and about 25% is dietary cholesterol. Cholesterol made in the body is called endogenous, and again, that's approximately 2/3 of total cholesterol. The body synthesizes approximately 1 gram, which is 1,000 milligrams per day. There are some nutrition books that have it around 800 milligrams to 1,500 milligrams, and then other nutrition books will say 875 milligrams a day. And there's a lot of literature out there that kind of averages it around 1,000 milligrams a day. Cholesterol from food sources is exogenous, and that is approximately 1/3 again of total calories. Dietary intake of cholesterol is somewhere approximately around 400 milligrams per day. There are some nutrition books that quote it around 180 to 375. There are others that will say around 500. So I've kind of averaged this around 400 milligrams a day is the dietary intake of cholesterol. Blood cholesterol is maintained at approximately 100 to 200 milligrams per deciliter. Dietary cholesterol is from animal sources. Now, if you have an instructor, professor that will tell you cholesterol is only from animal sources, and you have a test that asks you that question, answer it that way. There are some nutrition books out there that recognize that cholesterol does come from a minute amount from plant sources. And some of those, this is an article from the Journal of Chemistry Education, and it is from cholesterol and plants. And here's a link to that. It states that significant amounts are found in animal foods, up to 5 grams per kilogram, and less amounts found in plant foods, which is approximately around 50 milligrams per kilogram. So that's really not much. And in some nutrition books will recognize that plant cholesterol inhibits cholesterol absorption in humans. Now again, here's a link to that if you're interested in that. There are some reasons that some nutrition books don't recognize that cholesterol come in plant sources. Maybe it's previously the techniques that they use to determine this, or on food label packaging, the requirement to be considered cholesterol, it doesn't meet that requirement, so it just says 0 amount of cholesterol. So again, if your instructor says cholesterol is strictly animal, then answer that on your test. Okay, the 14 leading cholesterol-containing foods in the American diet. Now here, coming close to the end, I'll have the cholesterol recommendations. And they recommend it in between 200 and 300 milligrams. If you're healthy, 300 milligrams a day, and if you have coronary heart disease, it's less than 200. So as we can see here, beef liver has greater than 300 milligrams. Large egg yolk is greater than 200. Shrimp is almost 200. Beef, pork, chicken, and turkey all have 75 milligrams. Ice cream, trout, tuna, hot dogs, and cheddar cheese, they all have a good portion of cholesterol. And then you get to whole milk, which is 24 milligrams. 1% milk is about half that. And fat-free milk is about half that of 1%. And egg whites don't have any cholesterol. So the digestion of lipids. Predominantly, the digestion of lipids is in the small intestine. However, in the mouth, solid fats begin to melt at body temperature. The lingual lipase secreted from the base of the tongue, the sublingual salivary glands, they begin a little fat digestion and break down short chains of fatty acids. In the stomach, the gastric lipase secreted in the stomach is activated by the acidic environment, by the hydrochloric acid, and plays a small role in breaking down triglycerides containing medium and short-chain fatty acids. Again, the small intestine is the primary site for digestion of lipids. Cholecystokinin, a hormone that is secreted, it's synthesized in the small intestine. It is secreted in the first segment of the small intestine, the duodenum. It stimulates the gallbladder to release bile. The bile acts as an emulsifier, suspending fats in chyme while they are broken down by pancreatic lipase and intestinal lipase. The triglycerides are broken down as each of the 2 outer fatty acids are hydrolyzed individually. So a glycerol backbone will have 3 fatty acids, and it will take off the outer triglyceride first, and then the other triglyceride, leaving the middle triglyceride as a monoglyceride. So either the 2 free fatty acids and the monoglyceride can be absorbed, or 3 fatty acids are hydrolyzed, and a molecule of glycerol can be absorbed. Phospholipids are digested in the similar way. 2 fatty acids are hydrolyzed from the glycerol and can then be absorbed along with the remaining phospholipid fragment. And the phospholipid fragment is the glycerol, the phosphate, and the choline in the case of lecithin. The absorption of lipids. 95% of dietary lipids are absorbed. The digested short and medium chain free fatty acids, those are fatty acids that aren't connected to anything, and short chain monoglycerides, they diffuse easily into the intestinal cells and enter portal circulation. The portal circulation is the portal vein that goes from the intestine to the liver for processing. Long chain free fatty acids and long chain monoglycerides merge into micelles, which can then be absorbed into the aqueous intestinal cells. Once absorbed, the long-chain fatty acids, the glycerols and the monoglycerides, they will reform into triglycerides. Then the triglycerides, cholesterol, and phospholipids are packaged with proteins into what is called a chylomicron. A chylomicron is a lipoprotein, lipids and proteins. And chylomicrons are used for transportation of large fatty acids. So first, I'll show you a picture of a chylomicron, but first let me go through the enterohepatic circulation. First, the liver converts the cholesterol to bile. The liver will convert the cholesterol to bile, and then the bile is stored in the gallbladder. The bile is then released from the gallbladder into the small intestine to emulsify the fats. Then the bile is absorbed into the circulatory system where it is returned to the liver and it will be recycled. Some of the bile is bound to viscous fibers and it is defecated, lost in the feces. So this is a pictorial representation of the absorption, the digestion and absorption of triglycerides. So you'll have a fat globules, the big globule of lipids, and the bile salts will surround it, and that will become an emulsion. In the small intestine, in the duodenum, you will receive the lipase, the intestinal lipase and the pancreatic lipase, and they will break these large fat globules into free fatty acids and monoglycerides. And they will form micelles to take it through the aqueous intestinal lumen, and then the micelles will dissociate, and the free fatty acids will go into the intestinal cell, and they will reassociate, turning into a triglyceride. Added with protein, they will turn into a chylomicron, and that chylomicron will be secreted from the basolateral side of the intestinal cell and be taken up by a lacteal. That's the small capillary part of the lymphatic system. And that's how large fats are taken into the body. So transportation of lipids. Lipoprotein, again, lipoproteins, the chylomicrons pass from the intestinal cells into the lacteal for transportation through the lymphatic system. The lymph fluid and its lipids will flow into the thoracic duct and deposit to the subclavian vein, where the blood will carry them throughout the body for use or storage. Endothelial cells in the capillaries, in the small capillaries, they contain lipoprotein lipase that will break down the triglycerides as the cells throughout the body will need it. Body cells will extract the triglycerides, cholesterol, and phospholipids as they need them, and the remainder of the chylomicron, after it has delivered the cholesterol, the triglycerides, and phospholipids, it will be called a chylomicron remnant. Then that chylomicron remnant will be taken up by the liver, and it will be either broken down or recycled and degraded. So I have a picture of the classes of lipoproteins. But first, let me tell you about each one of these lipoproteins, and then I'll show you a graph that I have. The VLDLs, those are very low-density lipoproteins. They transport newly synthesized triglycerides from the liver to adipose tissue throughout the body. As the cells take up the triglycerides, the proportion of triglycerides and cholesterol shift towards cholesterol increasing in density, turning the VLDL into an LDL. So the very low-density lipoprotein, as it starts passing out all of its triglycerides, it will start to decrease in the triglycerides, and the amount of cholesterol it has will remain, but the triglycerides will decrease more than the cholesterol. So then the LDL will be, the VLDL will become an LDL. The LDLs predominantly transport cholesterol from the liver and, to a lesser extent, triglycerides and phospholipids to cells throughout the body for cellular membranes, hormones, and other compounds, and then returns the remains to the liver. HDLs, HDLs, they are synthesized in the liver, high-density lipoproteins. They pick up cholesterol from dying cells throughout the body, other cells, and they transfer cholesterol to other lipoproteins. And then they take the cholesterol from the body cells back to the liver to be recycled or excreted, defecated in the feces. So this is a graphical representation I have of the four classes. There is another one, an intermediate lipoprotein, but it is converted so fast that I'm not going to cover that. But we have the chylomicron, the VLDL, the low-density lipoprotein, and the high-density lipoprotein. Now what you see automatically real quick is the amount of triglycerides that is in the chylomicron. The chylomicron, again, takes the fatty acids from the intestinal cells and it distributes them throughout the body. So it has mostly triglycerides, 84% triglycerides, a little bit of cholesterol, a little bit of phospholipids, and almost no protein. It has 1% of protein, which relates the density. So when we relate to density, everything is related to the density of water, which is 1. And here a chylomicron has a 0.95 grams per milliliter, so it is a little lighter than water, and this will float in water. But this chylomicron, it is 100 to 500 nanometers, and this is not, it's not really a pie, it's a spherical shape just like the chylomicrons that I was showing you, with the phospholipid outside and proteins integrated into those phospholipids. Now this is a VLDL, a very low density lipoprotein, and that will take the triglycerides throughout the body. It is 50% triglycerides, and it is 22% and 18% phospholipids respectively, and a little bit more of protein. So as you see, the protein starts to increase, and so does the density. So the VLDLs, they are half triglyceride, as I said, and as they start distributing these triglycerides throughout the body, it will decrease in triglycerides, and the amount of cholesterol will be more than the triglycerides. So this VLDL will turn into an LDL, and the LDLs, they transport the cholesterol to the cells throughout the body. Here, cholesterol is 50% in the LDLs, and the triglycerides are almost gone, and it has a greater amount of protein, bringing the density to 1.01 to 1.06. And it is 18 to 28 nanometers. So it is a lot smaller from the chylomicron. And the HDLs, the high-density lipoproteins, here the triglycerides are gone, and now we are picking up the cholesterol from the body cells, dying cells, and transferring some cholesterol to other lipoproteins. And it contains a good amount of phospholipids. It's bringing stuff back to the liver. And it has a good percentage of protein, which is why it is the most dense. Now, I was curious about, this is kind of interesting, I kind of ask questions like this, but I was curious about the size of the chylomicron and the size of the high-density lipoprotein. So I asked a friend of mine, Professor Rolando Duran, a physicist at Florida International University, I kind of asked him which one is heavier, since the chylomicron will float in water and the HDL is heavier than water and it will sink. Which one of these two are heavier? So as a physicist, he said that's weight and is a different story. What we're looking at here is volume and mass. So he did two calculations for volume and mass on the chylomicron. He did two calculations for the volume and mass on the high-density lipoprotein. And again, I asked him, well, which one is heavier? So again, he told me that's a different story, but let me calculate this out. So he did a relationship between the HDL and the chylomicron, and it came up to where the chylomicron is 4.6 million times larger than the high-density lipoprotein. So this doesn't really represent a very good pictorial representation because the chylomicrons are huge compared to this. So again, I asked, is it heavier? And with the large amount of mass that the chylomicron has, yes, it is larger, heavier than the high-density lipoprotein. I just wanted to relay that to you. So lipids in foods. You know, going with the My Plate, there are lipids in every food category: grains, vegetables, fruits, dairy, and protein. Starting with proteins, you'll always find fats in marbled meat, bacon, poultry, especially in the skins, like the skin of the legs or thighs of chickens, deep fried fat, meats, and nuts. There's always fat in nuts. Dairy, whole milk, some yogurts, many cheeses, premium ice cream instead of low fat or ice milk. Fruits, this is added fats in fruit pies, and avocados actually have a lot of fat. Vegetables, deep fried potatoes, French fried potatoes, excuse me, and grains have added fat with crackers and pasta dishes with the added fat there. So what you want to do is sometimes you can't see the marbling in fat, the big fatty deposits or the surrounding fats around the meats. So you have to look on the nutrition facts labels. Look on the list of ingredients, and remember, control your portion sizes. Reduced fats foods, the calorie content is about the same. What they do is the sugar is commonly added in places of fat, so again, the calorie content is probably the same. Excessive trans fatty acid intake. What that does is it raises low-density lipoproteins. It lowers high-density lipoproteins, and it increases risk for cardiovascular disease. The current intake is 3 to 4% of total kilocalories, so that's about 30 to 40 kilocalories for a 2,000 kilocalorie diet per day. Trans fatty acids were added to food labels in 2006, and now they are required on the food labels. Excuse me. So to minimize the intake of trans fats, limit the use of hydrogenated fats, limit deep fried foods, limit high-fat baked goods, and limit the use of non-dairy creamers. Major sources of saturated fats: whole milk, cream, butter, cheese, sour cream, fatty cuts of beef or pork, coconut oil, palm oil, and palm kernel oil. The palm oil and palm kernel oil, they come from the same tree, excuse me. They come from the oil palm in Africa, and the palm oil actually comes from the pulp of the tree. And if it's pure palm oil, it will have a purplish color. Whereas the palm kernel oil comes from the seed, the kernel, and it is more translucent. The products containing these are such as candies, pastries, pies, donuts, and cookies. The 10 major sources of trans fats are deep fried foods: cakes, cookies, donuts, pastries, crackers, snack chips, margarine, imitation cheese, meat, and dairy products. When choosing margarines, choose soft margarines, liquid or tub instead of sticks, and read labels to avoid hydrogenated fats. You know, the difference between margarine and butter is that margarine is plant oils or fats, and the butter is mostly milk fats or cream. And coming up, I'll show you how we can manipulate some of these for fat substitutes. But let me continue. Oh, here we go. Fat substitutes. Okay. Using diet margarine, what they will do, they will add water to this. So again, there's a lot of room to manipulate in fat substitutes. And one of the ways is to add more water to margarine. And what the normal fat content of margarine is around 80%. Now, you can manipulate that, and the least is 65, but you can manipulate that to as low as 10%. And again, butters are more, less ability to manipulate those. So Z-trim is another fat substitute. It's produced by the USDA. It is a starch derivative that binds with water. So the starch, the soluble starch, viscous starch, will bind with the water, and it will act. It will increase the bulk, and will act as a fat substitute. Again, fiber cellulose, the insoluble fibers, are in malt trim, stellar, and oat trim. And dairy low, it is a modified whey protein concentrate. I must interject. There are several ways to manipulate fat substitutes, and those are through carbohydrates, proteins, and lipids. So we did the two carbohydrates, the Z-trim and the malt trim, stellar, and oat trim. And the way to manipulate with proteins is the dairy low, and there's other products out there. But they use the proteins, and the protein, this is used with a modified whey protein concentrate. And they are fat globules. They are surrounded by, again, phospholipids that help them as an emulsifier. They emulsify them in the fat phase. So it helps act like a fat substitute. Now, olestra and olein, these two are, the last two are using fats to manipulate fats, so to speak. Olestra, the trademark olein, it is not digested. It is a very large fat, and this is a compound of olein. What it does is it links fatty acids to sucrose. And if you remember, sucrose is a glucose monosaccharide and a monosaccharide of fructose. So this is a sucrose molecule, and they hook up these fatty acids to it. And since it's so large, it is not digested. It was FDA approved for fried snack foods, and it may cause some intestinal problems and diarrhea. And it has some fat-soluble vitamin issues. Since it is not absorbed or taken in the body, you may lose some of the fat-soluble vitamins. Solid trim, the trade name Benefat, they are long and short-chain fatty acids. This is a molecule of Benefat, and what they do is they manipulate the fat. So what they do is they take off the longer chains of fatty acids, and they use either 2, 3, or 4 carbon chains, such as acetic, propionic, or butyric acids, 2, 3, and 4 carbons. And then the longer carbon chain in the middle, that is steric or palmitic. That is 16 or an 18 carbon saturated fatty acid. Now, both of these are poorly absorbed. So with the decreased short chain fatty acids, that will decrease the calorie content. And since the long chain is poorly absorbed, the calorie content of Benefat is about 50% of a normal fat. The health effects of lipids. HDLs, they remove cholesterol from the bloodstream, as we just went over. The HDLs, they may block oxidation of LDLs, which reduces the risk of cardiovascular disease, and premenopausal women have higher high-density lipoproteins. There are scavenger cells. They are white blood cells. They are in the circulatory system, and they are either floating free, excuse me, they're either floating free, or they are built up upon the arterial walls. And what they will do, they will remove the oxidized. What happens is that the double bonds are broken, and then you'll have shorter chains of broken down fatty acids, and they will remove those from circulation. And if they're absorbed into the scavenger cells on the arterial walls, that will lead to a plaque buildup on the blood vessels and leads to atherosclerosis. And also, blood vessel damage is caused by smoking, diabetes, hypertension, high homocysteine, and high LDLs, and infection. Now, antioxidants, they reduce the oxidation of these fatty acids, as these mono or polyunsaturated fatty acids, and it will slow the low-density lipoprotein uptake by these scavenger cells. The recommendations of lipids. There is no RDA for fat. We're not trying to say that we want you to get a certain requirement of fat. We are trying to say that we want you to limit specific fats and increase the mono and polyunsaturated fatty acids and essential fatty acids. So the acceptable macronutrient distribution range is in between 20 to 35% of total calories, and that's around 400 to 7 kilocalories per 2,000 kilocalorie diet a day. The American Heart Association, their recommendations are 25 to 35% of total calories from fat per day, and that is in between 500 to 700 kilocalories, again, on a 2,000 kilocalorie diet per day. They recommend less than 7% can come from saturated fatty acids in a day, and that's equal to about 140 kilocalories, or approximately 16 grams in a 2,000 kilocalorie diet a day. And they also say less than 1% from trans fatty acids per day, and that's less than 20 kilocalories, or around 2 grams per 2,000 kilocalorie diet per day. So you really have to watch the trans fatty acids. Again, the hydrogenated fats, look at the labeling, the packaging. And they recommend 300 milligrams of cholesterol a day for people without coronary heart disease. And if you do have coronary heart disease, it is less than 200 milligrams of cholesterol per day. The average U.S. intake is 30% of total kilocalories from fat, 13% of kilocalories from saturated fat, and approximately 180 to 320 milligrams of cholesterol per day. Now, the Food and Nutrition Board, the recommendations for essential fatty acids, here's a little chart that the recommendations of these essential fatty acids, the omega-6 and omega-3 fatty acids. The linoleic acids for men is 17 grams a day, and for women is 12 grams. That is, for men, 153 calories, and for women, 108 calories per day of the omega-6 fatty acids. For the omega-3 fatty acids, that's just over a gram and a half a day, which is approximately 14 kilocalories. And for women, it's a little bit over a gram. And that's just about 10 kilocalories a day. So that's not very much. What I have here is a small graphical representation of the amount of omega-3 fatty acids in 3.5 ounces of fish. And as you can see, the salmon has almost, now this is farmed Atlantic salmon, and they also have wild Atlantic salmon. Different salmons have different contents of omega-3 fatty acids, but what I'm pointing out here is that it is in between 0 and 2 grams. So you're going to get a good piece of fish can give you the requirements for a day of your omega-3 fatty acids. So, and again, this is in between 0 and 2. We have fish, tuna, swordfish, which is just about 1 gram, shark, king crab, which is about half a gram. So again, if you were to combine both the omega-6 and omega-3 fatty acids per day, it's approximately 7% for men and about 5% a day for women with a combination of the omega-6 and omega-3 essential fatty acids. Okay, more recommendations. The National Cholesterol Education Program and the Food and Nutrition Board, they recommend 35% of total kilocalories from fat. The reason it seems a little high, 35%, is because they want you to keep your saturated fat, cholesterol, and trans fats to a minimum. So if you increase your essential fatty acids, you can work up to that 35%. Eat plenty of fruits and vegetables. I had a professor that would always say, anytime she dealt with fruits and vegetables, she would say 5 a day fruits and vegetables. Cut down on red meats, cut down on simple sugars and refined carbohydrates, promote healthy weight, and be active. It speaks millions to be active. Okay, cardiovascular disease. Excuse me. Okay, cardiovascular disease. This is a coronary artery that supplies the blood, the heart with blood. And a normal coronary artery will look clean. As the scavenger cells on the arterial wall start collecting the oxidized LDLs, the plaque starts to build up and you start to form atherosclerosis. And then you'll have a blood clot build up, and that will occlude the lumen. And then this portion of the heart will die, and that leads to a cardiovascular disease, which is a heart attack, which is considered a myocardial infarction. Now, there are a couple different cerebrovascular diseases, such as stroke and hemorrhage. But the risk factors for cardiovascular disease, and that is total blood cholesterol greater than 200 milligrams per deciliter. Smoking increases clotting, and it increases the expression of a genetic link. So smoking will cause mutations in your genes, and then it will start to express these genes into a cardiovascular disease. It's very detrimental. Hypertension greater than 135/89 millimeters of mercury. Diabetes, insulin increases cholesterol synthesis, and it guarantees the development of cardiovascular disease. The risk factors for CVD is low HDLs less than 40 milligrams per deciliter. As age increases, so does your probability of plaque building on your artery walls. A family history of cardiovascular disease may increase your propensity to have CVD. Blood triglycerides greater than 200 milligrams per deciliter. Obesity, fat around the waist, and insulin resistance. The insulin is just not pulling the blood into the cells, and inactivity. Again, signs of a heart attack: intense, prolonged chest pain, shortness of breath, sweating, nausea, vomiting, dizziness, weakness, jaw, neck, shoulder pain, and an irregular heartbeat. Medical intervention: for those who have experienced a heart attack or have cardiovascular disease or diabetes. This is a link to the National Heart and Lung Blood Institute from the National Institute of Health, the government, and it is a very diverse website. It has a lot of information, so if you fall into any of these categories, it has some good information for you. Medication to lower low-density lipoproteins. They reduce cholesterol synthesis. They are statins such as Lipitor, and what they do is they reduce the HM-CoA reductase. That is an enzyme that is needed to produce cholesterol. And then there's also natural treatments such as niacin. This is a link going to PubMed that tells you about how niacin will work in binding bile acids and preventing the recycling, leading to elimination. They prevent the recycling of the enterohepatic circulation of bile acids. So it decreases cholesterol synthesis and in the body, in the blood. Medication to lower blood triglycerides, they reduce triglyceride synthesis. Lowering low-density lipoproteins. See your doctor to assess for other conditions. Reduce your dietary saturated fatty acids and cholesterol. Increase your monounsaturated fatty acids and your polyunsaturated fatty acids. Increase dietary fiber, the soluble fiber, the viscous, the pectins, gums, and mucilages. Lowering blood triglycerides. Triglycerides are the most diet-responsive blood lipid, so you can alter your blood triglycerides. Avoid overeating. Limit alcohol. Limit simple sugars. Consume small, frequent meals throughout the day, and include fish in your diet at least 2 times per week. Decreasing blood triglycerides. You can use plant stanols, they're sterol esters. An example of these are Benecol and Take Control margarines. They have cholesterol-lowering effects. They decrease absorption of cholesterol, and they lower the amounts of bile salts returning through the enterohepatic circulation. And the liver takes up more cholesterol from the blood, and it is lost in the feces. Okay, how to increase high-density lipoproteins. Physical activity is important. It is just important as your diet. It does wonders for diabetes, cardiovascular disease. Physical activity at least 45 minutes per day and 4 days per week. Don't smoke, eat regularly, eat less total fat, and moderate your intake of alcohol, and that will increase your high-density lipoproteins. Okay, desired blood lipid profiles. This is where you want your blood lipids to be. HDL cholesterol, you want it to be greater than or equal to 60 milligrams per deciliter. Low-density cholesterol, low-density lipoprotein cholesterol, you'd like that to be less than 100 milligrams per deciliter. Triglycerides, you'd like to be that less than 150 milligrams per deciliter. And again, total cholesterol, less than 200 milligrams per deciliter.